shoe factory that was down here in Brockton, Massachusetts in 1905, the first part of 1905. And they had a problem in that their boiler blew up. And it turns out you can see a smokestack back here in the background. So this is the before picture, here's the after picture. Okay? So here's the smokestack in the background, and here's the building right here. Okay? Now it turns out that this was not exactly the first boiler explosion. There was a, in the 1830s, near Cincinnati, they had a steamer, paddle wheel type of steamer, that blew up and killed 230 people or something like that. And that led to the first government research contract in the United States, which was funded by the federal government. And they gave some money to the Franklin Institute in Philadelphia, Pennsylvania, to try to figure out why the boiler blew up. Okay, now, those guys didn't understand anything about brittle fracture, quality of steels. Actually, probably wasn't even steels, it was probably a cast iron boiler so far as that goes back in those days. But when you have lots of stored energy in terms of a pressurized gas, it can do a lot of damage. As a result of this particular explosion in the Brockton, Massachusetts shoe factory in 1905, the American Society of Mechanical Engineers started to develop some rules for designing and building pressure vessels. And that ended up in 1914 as the first edition, and this is not the first edition, I don't happen to have this first edition, of the Boiler and Pressure Vessel Code. This happens to be Section 9 of the code. This is my only, I mean, they charge about $2,000 for the code. So this is my 1989 version. But this just tells you, with its addenda and stuff, how to make, how to qualify welders, okay? It doesn't tell you anything about design. If you want to know something about design, you go to Section 3, this is Section 9, and so there's, this is, there's 10 sections to the code, so you've got 10 notebooks about this thick today for the code. Section 3 tells you how to design nuclear vessels. Section 8 tells you, it has a Division 1 and Division 2, it tells you how to design other types of pressure vessels. I can't remember, some of the others are boilers, and I don't deal with designing boilers very often myself, but in any case, there's a difference between a boiler and a pressure vessel. A pressure vessel is basically an unfired, it's not fired. By fired, they mean you're putting heat into the vessel, okay? And this all goes back to basic thermodynamics type of stuff, because it is American Society of Mechanical Engineers. But this book right here is ASME Section 9. It's a standard code has rules for qualification of welders. It doesn't actually tell you how to weld different types of materials, but it tells you certain types of rules. In fact, the code is just full of wonderful little tables. I guess I can show you how exciting this code is. Okay, this goes on, whoops, this type of page. Let's have to pull one up. Table QW 2422, which is qualification for welding, is QW, and it has what they call P numbers, and there's virtually any type of steel you can think of here. And if you go past steels, you'll get into stainless steels, you'll get into aluminum alloys, you'll get into cast irons, you get into all kinds of things. It takes a lifetime or more to understand a set of rules like that. It turns out that the rules, the federal government doesn't adopt the rules, but virtually every state, in fact I think all 50 states, have adopted the Boiler and Pressure Vessel Code in one way or another. Now, so that's kind of an addendum. Let me show you one other code. The other code that's used most often, I showed you the other day, is AWSD 1.1, the Structural Welding Code, and this has similar types of exciting tables. It has, this actually is sort of an abbreviated version. It's different than this code, but this is the ASME code section Section 3 and Section 8 and some of these others will be sections on individual design issues. This has a chapter on designing bridges and buildings and tells you what the allowable stresses would be. But this is just for steel. It turns out there's versions of this for aluminum. Okay. There's versions of this for let's see, what other codes do we have? Reinforcing steel. Okay, this is rebar that goes into concrete. It turns out that particular type of steel is much more difficult to weld than most other things. And they also have specifications. You can tell if it's red from the American Welding Society, it usually has to do with specifications and whatnot, or welding procedures for different types of metals. However, if I get to steels, the major problem in welding of steels, I told you last time, that steels are actually very easy to weld. The major problem is some form of hydrogen cracking. We talked about that last time. And you have to have three things to get hydrogen cracking. You have to have a source of hydrogen, you have to have stress. Actually, many people will point out you have to have tensile stress. Compressive stresses don't do it. And you have to have a susceptible structure. And for steels, you can kind of think of this as how hard is it? What's the hardness level of the steel? The harder the steel, the stronger the steel, the less hydrogen it takes to cause cracking. They didn't really have serious problems in welding submarines in World War II because those submarines only went a couple hundred feet deep, for example, just kind of to get out of the way of the surface ships. Today they go considerably deeper, and if I told you how deep they could go, I'd be lying because I don't know officially. But you can figure out if the wall thickness is on the order of a couple of inches and it's 30 feet in diameter. You can kind of figure out collapse depths and things like that. And you know it's well in excess of 1,000 feet. It's not in excess of 5,000 feet, but I'll just kind of tell you it's well in excess of 1,000 feet for a submarine today. And in order to do that, in the 1950s, they went to higher strength steels. And in the 1960s, they went to even higher strength steels. And now in the 1990s, they went to even higher strength steels. As they do that, they get higher and higher hardness. And generally, depends on what code you look at, people look at a Rockwell hardness and on the C scale of either 22 or 30. If I'm in the pipeline industry, I don't want to see a hardness above 22, Rockwell C. And if I'm in high strength steel business, like 100 KSI steel would be Rockwell C30. The reason for this is, turns out it's hydrogen sulfide cracking, which is just another form of hydrogen cracking. So you have to have a source of hydrogen, a source of stress, and a susceptible structure. Well, steels, depending on their composition, will give you various amounts of hardness. And I showed you last time some pages out of the back of Stout and Doty, which is kind of from 1945 to about 1980. This was sort of one of the main books to look at the weldability of steels. So virtually any steel you can think of, in fact they have an index to this index. So here's the index right here of all the different ASTM steels, okay? And it goes on for pages, and then it's got the SAE steels. Every one of these numbers represents a different steel. And then you have individual procedures going on for pages and pages, and what they give you in these individual procedures is the name of the steel, the type of steel, the thicknesses of the steel, because that in fact influences the cooling rate of the steel. The cooling rate will influence the hardness. What the preheat should be. It turns out, I think I mentioned hydrogen diffuses out sort of like It's the same kind of same speed as you lose the CO2 after you open up a can of soda. You have to worry about it every few days. In this structural welding code, the highest strength steel you can use is 100 KSI, okay, for bridges and whatnot. But if I'm going to do testing on that, that's going to be a Rockwell C30. It's going to be susceptible to fairly susceptible to hydrogen cracking, and excuse me. It's going to be susceptible to hydrogen cracking, and they won't let me do the non-destructive testing until 48 hours after I finish the weld, just in case I have delayed cracking from hydrogen.
I have a question about all these codes and everything like that. How practical is it that, you know, the person who's welding these bridges and buildings and stuff has any idea what that's?
The actual guy holding the electrode doesn't understand these codes much at all. Very few of those people even have seen a copy of the code.
So
there's some welding engineer.
You know it and check your work, is that basically what it is?
You have inspectors who are supposed to know the code, because there's whole sections in here on welding inspection. Okay, there's a chapter. Well, actually, who uses the code? If you go through the table of contents of the code,
Lawyers probably, right?
well, yeah, so something goes wrong. That's general requirements, which basically just says, you know, who's responsible, definitions of who's the engineer, okay? Who's the contractor, who are the inspectors, okay? The engineer is the designer, in theory. And so chapter 2 is on the design, and it tells you how much stress you can put on welds, okay? So 2 is design of weld connections, and it has it for tubular connections and non-tubular connections, which means high beams and things. And chapter 3 is pre-qualification of the welding procedure specification. Okay, since you asked this question. A WPS, and this is also in the ASME. Okay, you have to have a welding procedure spec. Now, the engineer will call out, and should be on the drawing, what type of weld they want to put on there. That's the engineering designer, the structural engineer. He's going to design the building of the bridge. He's going to say, use this size I-beam, weld it here, do a full penetration weld, do a partial penetration weld, do a fillet weld, make it this size, okay? He then ships it off to a fabricating shop. A fabricating shop will then do what they call the detailed design. So first you have the design. Mixed up here. So you have the structural design. And that's the guy who wants to know what the stresses are, okay? And then they send it out to the, for detailed design, and that goes to a fabricating shop. And that may have some engineers, some welding engineers. This would be a structural engineer, like a civil engineer, or mechanical engineer. This may have some engineers, but they'd be closer to a welding engineer. And that guy's going to go to the code, and he's going to say, okay, and this is going to be the fabricating shop, okay? So this is the engineer or architect. This is the shop that's actually going to do the fabrication. So the fabricating shop basically goes through and looks at this overall drawing, and they do a detailed drawing, sometimes called shop drawings, okay, because they're the shop that's going to fabricate it. This guy did the architectural drawings, and this guy's going to do the shop drawings. The shop drawings are going to be the same thing, but they're going to have much more detail. They're going to go in there and say, you're going to use this WPS. And this WPS welding procedure specification belongs to that company. Okay? And what it means is that company did a set of test welds, and it tells you in chapter 3 how to do these test welds. And that company will submit those test welds to another company, a testing company. And the testing company is generally independent. And we also have up here, I'll call it up here, you have the owner. Okay, person purchasing. So they hire an architect or an engineer to design it. The architect and the engineer turns it over, It could be these people could take responsibility for the owner to take care of these people, or it could be the contract directly here. Okay, there's lots of different ways to do it. But these people have developed a procedure, a recipe for making a given shape weld in a given type of steel. And it all follows the ASME welded pressure vessel code or the structural welding code. If you're talking about a pressure vessel, it's going to by law come under the ASME code. If you're talking about AWS 811, it might be written into the local law, building codes. More and more it is. And if you went back 25 years ago, not necessarily. But more and more states are now calling out in their building codes, you have to weld to D11. So this is a detailed specification. It tells you what travel speed, what type of electrode, what type of preheat, and it tells you the recipe for making a good weld. The next thing that's in there, there'll be a procedure qualification record. And until recently, until the last 10 or 15 years, these WPSs were owned by the company. It costs you about a couple of $1,000s to develop one of these things. And that becomes one of your assets of your fabrication company. No one else can use your WPS. Until more recently, in the last 10 or 15 years, the American Welding Society has been developing welding procedure specifications that anyone can use in the country. And in fact, in the code nowadays, they have what they call pre-qualified welding procedures. Okay? So there are some that anybody can use, but more complex ones the company has to qualify. The procedure qualification record means they actually go out and weld a plate and send that plate to this testing laboratory to have them break it, x-ray it, whatever the sets of tests are that are all specified by the code. Okay? That says our recipe works. Okay? And then there is the welder qualification test, where the individual welder, not the recipe, but an individual person, actually shows that they have the mechanical skill to be able to put down sound weld mount. Anybody here a qualified welder? Ever been a qualified welder? Nor have I ever been officially qualified. I guess that means that I have the best chance of actually being able to pass one of these tests, weld up a plate. So here I weld up a plate to prove that the recipe's good, and I have one of my best welders do that. Every welder who's going to go out there and weld, before I can send them out on the job, has to do a test of proficiency, which goes to this testing laboratory. They independently evaluate it. Okay? So it's kind of a long-winded answer. There's PQRs, WPSs, welder qualifications. It's all spelled out in here. Okay? And then finally, there's the inspection of the structure. And that could be the same testing laboratory, it can be another testing laboratory, but typically it's an independent testing laboratory. So you got owners, you got structural designers, you got fabricating shops, and you got testing laboratories. And they all interact. And when something goes wrong, they're all pointing at each other, or as the guilty party. Does that answer your question?
Yeah.
In more detail than you wanted, right?
I worked at a place that went on strike and they had me welding for my senior internship. They were just like, here's how you do it.
Oh wow, but they probably weren't doing code quality welding, or they would have had to qualify you.
I don't know, they were making like large HVAC systems.
Yeah, but HVAC doesn't come under any specific codes.
Okay.
Okay. And there's specifications rather than codes, or recommended procedures. I mean, so there are codes, which often, codes are written by private entities, unless you happen to be in the U.S. Navy, they write a code. But mostly they're written by societies, like the Welding Society or the Mechanical Engineering Society. These are often written into law. So they're adopted by public agencies. Then you have specifications, which are lower than codes, and the specifications basically say, we've written up something. This is specification for fusion welding for aerospace applications. And so a bunch of people in the industry got together and wrote up some rules that if I'm the owner, I can call out the specification, but a public agency doesn't do it. So the owner can specify a code and a spec. Actually, the structural designer usually does this or this. Fabricating shop doesn't. They'll be told by one of these two people which code or which spec to follow. Okay? And these people will be told which one to test to, because there'll be rules for testing. There's a chapter in there on inspection, and it tells you what's acceptable and what's not acceptable. If you don't specify a code or a spec, there is no qualification, there is no standard which you must follow. So this is actually, code is the highest level, specification is just kind of an industry consensus document that an owner or a designer can call out and say, we want you to follow this. There's no force of law if you don't, but we want you to follow it. Or if there's a code, you use the code. And the last thing is a recommended practice. And I don't know if I got any recommended practices here. Well, actually, I guess let's take it back. There's recommended practice, and then there's a guide. Okay. A recommended practice is guys in the industry have written together a little book, and they're not even glorifying and calling it a spec. They're saying, well, this is what we recommend you do. And a guide means it was probably written by one or two people rather than a whole group of people. It doesn't have any sort of consensus to it, but some people who are generally knowledgeable in the professional societies decided it's a worthwhile thing to make available to people. So a guide just kind of you go to, and it's good practice, not necessarily recommended practice, or some practice that other people have found to be good, I guess maybe is one way to say it. So you got all this complexity and all the contracting and stuff, but getting back to steels and how to weld them, there are other problems in welding steels that have to do with the cleanliness of the steel. But in general, the composition of the steel, if it's high in carbon, it will tend to have a high hardness. Carbon is what makes steel strong in general. You add other alloying elements that allow you to get hardness to greater depth into the steel. So if I have a 1/4 inch thick piece of steel, I can just go with the carbon steel. If I got a 4 inch thick piece of steel, I've got to add some alloying elements to slow down the reactions with carbon so that when I'm heat treating that steel, I can get the high hardness and the high strength. Okay, so there's a difference between hardness and hardenability, okay, in steels. Hardness is how much stress it can support without breaking, or it's directly related to it. Hardenability is how thick can I get that kind of hardness, okay? What's my ability to heat treat it in thick sections is hardenability. And I throw all these expensive alloying elements in order to get hardenability to greater thicknesses. For example, a 1040 steel, just a simple plain carbon steel, I probably can't get uniform hardness through the thickness over more than about 1/4 of an inch. But a 4340, I can get it over 4 inches. Okay? And there's a 4140 in between, it has less alloying element, I can probably get it up to 1 inch. And that's one of the reasons we have so many steels around, because they have different amounts of hardenability. These all have 0.4% carbon, and so they will come up with roughly equivalent hardness, but in different section thicknesses. This is one of the most difficult steels to weld. This is medium, okay? The lower the carbon, the easier it is to weld. A 1008, which is what we used to make automobile bodies out of, if you can't weld 1008, you really ought to go out, get out of business, okay? Because it's not much more than iron with very little amount of carbon. It's basically almost pure iron. Put a little manganese in and silicon to improve, give resistance to oxygen and sulfur, but other than that, it's mostly just a low carbon iron. Yeah.
What are the alloying elements for the 4340?
Nickel, chrome, and molybdenum. Okay, and 4140 is chrome and molybdenum. Nickel gives greater hardenability, but it's very expensive. 4140 is chrome and molybdenum. You can look all these up in a book like Stout and Doty, because good old Stout, Mr. Stout, if you go across This is a table that goes across to the second page. And on the second page, they actually give you the composition of the steels: carbon, manganese, silicon, nickel, chrome, moly, other. Okay? And it will tell you the tensile strengths of the steels. So I can get down here, I have can't read it that well, a tensile strength of 47,000. Up here, I'm at 105 to 135,000. I mean, I can have a factor of 3 variation in the strength of the steel. Okay? But if I go back over here, for a given set of steels, it will tell me what type of preheat temperature. How much do I have to heat the steel up to drive the hydrogen off just after welding so that it doesn't do the damage within that first 48 hours? Okay, if I preheat it, depending on the thickness, I have to preheat it to higher temperatures. And whether I use hydrogen, low hydrogen, or other than low hydrogen. What do we mean by hydrogen other than low hydrogen? Well, after Westinghouse and Edison made electric current easily available, people started doing electric arc welding. And they started doing it with just simple steel wires. And if they did that, they ended up getting Swiss cheese for a weld. Am I talking about this? Okay. The reason you get Swiss cheese for your weld if you just weld in the air in electric arc, because you get nitrogen from the air, it gets into the steel, and liquid iron will dissolve lots of nitrogen. But on solidification, it rejects that nitrogen because the solid steel does not dissolve very much nitrogen. So you get these bubbles coming out. It's just like your soda again. Okay? If you were to take your Sprite and freeze it, you'd find it would get flat as soon as you freeze it because it would drive off the CO2 as it freezes. Okay? Well, it drives off the nitrogen and leaves Swiss cheese behind. And in fact, I think I sent around a little plastic weld that had a bunch of porosity. They lost their shielding to keep the atmosphere away, and that you saw the Swiss cheese that was on the end of that thing. I guess I can bring it back in next time. Well, it turns out that was the 1880s, and then around 1910, in one case in Gothenburg, Sweden, and the other case in the United States, people learned that if they took those bare wires, and in Gothenburg, the guy found that if he stuck it in the mud, now if you go to the Aesop Wells website, you won't find the story quite this way. But basically, the guys found that if they put a mineral coating on the electrode, and the story is the guy actually stuck it in the mud and welded with a muddy electrode, and he found that the mineral flux provided enough of a shielding atmosphere and a little glass layer on top of the weld to protect it from the nitrogen in the weld, and you got 100% dense weld. And that was the beginning of the Aesop company, and that's what we call mineral-coated electrodes. Today, you have these 14 to 18 inch long electrodes, depending on their diameter. Actually, they get to be bigger. I'll show you that in a second. And you'll see it on Thursday, but you grab it with some copper tongs, you put a welding helmet, you do a scratch start, and you strike your arc and you weld. And they learn to do that. Now, this particular flux, and I don't know if you'll be able to see it or not, this particular flux is mineral coated, and they've done everything they can. They heated this to about 700 degrees to try to drive off all the moisture. And this is the type of electrode that if you go through, or they actually heat up the electrodes and keep them warm, okay? You check these out at the shop, at the fabricating plant, out of the tool room, and they kept them hot in an oven at 200 or 300 degrees. In some cases, they actually give the welder a little portable oven they carry with them with this really critical steel that will crack very easily if it gets any hydrogen. This has a fairly brittle coating. You can see it just comes off. And actually, I have another thing. Actually, it's on the website. I can show you that actually shows a little dust coming up. This is a cellulosic electrode. In the United States, and I don't know who the person was, but some guy found that if you wrap paper around the bare electrode and he burned off the paper at the same time, it's called cellulosic electrodes, they generate huge amounts of hydrogen. So you have to be very careful, and that's why Stout & Doty has low hydrogen, which would be the mineral coated electrodes, and it has other than low hydrogen, which means high hydrogen. Cellulosic, this stuff is about 60% paper, and I can bend this thing without it cracking until I get a 90-degree bend, and then it comes off in chunks. Okay. Different types of coatings, different hydrogen potentials. The other than low hydrogen, you're actually welding in a 60% hydrogen atmosphere. It's very reducing, but it loads up the steel with hydrogen, could lead to hydrogen cracking if you have high hardness and you have a high tensile stress. So this stuff gets very complex. It's good for me, good for business, because people screw up every now and then. But there are recipes. These basically, when I have to write welding procedures, I'll often go to Stout and Doty, and it kind of gives me some of the recipes that people have found. But companies will come to a welding engineer and say, we need a welding procedure to weld this particular part. Okay? And so you have to write up one of these things. And this welding procedure can be 1 page, or it could be 10 pages long, depending on how complex the recipe is. Procedure qualification records, typically a couple of pages. You actually weld the plate, send it out to the test lab, hopefully pass the test, radiography, bend test, make sure you don't have any cracks, whole host of tests, okay? If it passes, then you have a qualified procedure. Then you have to have the welder prove that he can make the thing. Now, fortunately, and this was actually sort of right before World War II, people were sort of learning what was causing cracks in steels. And they came up with things called carbon equivalent formula. And here, this is out of a welding book. It just gives a bunch of different formula. This is the appendix table. And let me blow up the carbon equivalent formula. There are many different, the point of this thing is just show you the many different carbon equivalent formulas, but it's equal to the carbon equivalent is going to be related to how hard can that steel get during the welding process. The higher the hardness, the greater the susceptibility to hydrogen cracking. And the carbon equivalent is equal to the carbon plus the manganese divided by 6 plus the chrome moly and vanadium divided by 5 plus the nickel plus carbon divided by 15. Here's another formula where people have different things. These are just empirical formulas that people have derived. Nowadays, people like to use this PCM formula because the steels that have been designed in recent years follow that better than some others. This next thing, this is actually a figure out of the structural welding code. And this was developed by Brian Gravel. It basically says, here's your carbon concentration, your carbon content, and I said a 0.4 carbon steel is fairly high carbon. 0.008 or 1008 is down here, very weldable. Here's your carbon equivalent, here's your carbon, so you're plotting the two, and anything below a 0.1% carbon is very weldable. It's almost impossible to cause hydrogen cracking. Here's zone 2, higher carbon, but lower carbon equivalent. Doesn't have a lot of alloying elements. So here's your 1040 steel right here. Okay, 1040 steel would be right about there. Not too bad to weld. 4340 is going to be way up here in zone 3. Terrible to weld. Okay, so this basically gives you different regions. This is written into, as an appendix, that chapter. There's a whole appendix of about 10 pages in here telling you under what conditions of tensile stress, hardness, and carbon, and type of welding electrode, essentially those 3 parameters, you can come up with a good procedure, a good WPS for welding a given steel. Okay? What else do I want to say about welding of steels? Talk about stout and doting. Oh. Here's specification for fusion welding in aerospace industries, industrial and mill cranes. I mean, people have gotten together because mill cranes, essentially well, first of all, they're a critical structure. If you lose a mill crane, you often kill people if something falls on them. A lot of this comes directly out of the structural welding code, but it's basically a specification that people have written for how to repair those cranes. This is specification for welding and rotating elements equipment. Remember I showed you the fan shaft? This was the code, not the code. This is the specification. It's not a code for welding of fan shafts. And it goes through and it tells you all the different types of steels. Similar types of things, but not as elaborate because it's not as old. Here's structural welding code for aluminum. We'll talk about that in a second. But, reinforcing steel. Reinforcing steel has very high carbon. In fact, reinforcing steel is sometimes off the diagram up here. Okay? So there's a special code for it. It makes it very difficult to weld. And in general, should not be welded. Well, I shouldn't say that. It can be welded, but you have to know what you're doing. And this is just a simple concrete rebar. Now, I've had a number of concrete building failures because if your rebar is cracked, you don't have that tensile strength for the structure. And I've had situations where people, well, what you're supposed to do in most cases is you're supposed to wire the rebar together. You can bend it, and you know you've seen the formworks of the rebar. And nowadays the rebar is typically sort of green. Anybody know why it's this kind of ugly lime green? Anybody see it? Seen it? Okay, on the highways and stuff. That's an epoxy coating. And what happens to the rebar? Actually, when I was an engineer at Bethlehem Steel in the mid-70s, people were getting all concerned about this. The highway bridges, and you have to remember, we built a lot of highway bridges starting in the 1950s with the interstate highway system, the Eisenhower system. Anybody know why we built the interstate highway system?
We needed jobs.
Well, it was a good jobs project. It's been a great thing for infrastructure, but it was actually sort of a military project because they wanted to be able to move missiles around if those Ruskies shot at us with atomic weapons. Okay, so we decided we needed a good highway system to be able to have portable missiles so we could fire back. Anyway, so the rebar is inside the concrete like this, and it turns out over time, moisture, particularly in the Northeast or in the northern climates, you'll put road salt on the highway, and the chlorides will get through here, will form an iron chloride oxide. Rust, if you will, which expands in volume and causes the concrete to fall off. Just breaks the concrete because it's generating the internal pressure. And so nowadays people actually coat the rebar with epoxy to try to protect it and give it greater life. But basically what was happening in the mid-70s, after 10 or 15 years into building all these highway bridges, they were falling apart. And then by the 1980s we started putting epoxy coatings on things, and today that's what you usually see. But in general, so actually it's harder to weld the rebar because you can't weld over the epoxy, you have to scrape it off. And you have to preheat it. Rebar typically is not preheated 100 or 200 degrees. You typically have to get up to 400 or 500 degrees. In fact, there's a nice little table here. Here's the carbon equivalent formula. Permissible stresses in the rebar, showing that the stresses are important. And let's see, minimum preheat and interpass temperatures. You don't have to worry too much about this, but you see, depending on the carbon equivalent, you can be up to 500 degrees Fahrenheit. This is actually not a bad table to show you that if you have low carbon equivalent, you don't have to do any real preheat. 50 degrees Fahrenheit, just drive off the ice. And as the carbon equivalent goes up, the preheat temperature goes up to keep it from hydrogen cracking. That's for reinforcing steel. But it's true for virtually any steel.
Why do you even want to weld rebar?
Well, you got to hold these things together. You're trying to make a three-dimensional cage, and the easiest thing would be there to go in there and tack weld it. But in fact, what they should be doing is wiring it together.
Right.
So you lay it in. You might have to have a crane hold it while a guy goes in there and does this. If you could go in there and the guy could just tack weld it, piece of cake. Okay, he can tack weld faster than he can wire tie. So you like to weld rebar just to hold the frame together before you pour the concrete. Well, I've seen a number of cases. In fact, the first case I dealt with was Dan Rather's new newsroom in about 1980. In New York City, they were adding on to the CBS building. And they were building a new newsroom for Dan Rather. And they're going to have beams going across. There was a steel structure, but they had reinforced concrete beams kind of holding the window sockets and things. And they noticed that some of the beams, after they cast the concrete with the reinforced rebar in there, were sagging a little bit. And then one day, while they were working on it, the whole front of the building came down. And it turns out it was the concrete rebar, and they had little cracks from hydrant. They tack welded it against the code. Okay, they've done it illegally, because actually New York City actually called it out and said, you know, New York City had some pretty rigid specs. And they developed little hydrogen cracks, and it's a brittle material, high hardness, and these things under stress just snapped. And once you got, we had like 4 rebar across the bottom that took the tensile stresses on the beam. And those, once you got, I think you had to have at least 2. In some cases, we had a third that were broken, all within a foot length of each other, and then the whole thing came down. And so one of them came down, and then it was the dominoes, you know, taking all the rest of them down. But I've seen it a number of times. Someone comes in and hack welds the rebar. Not that you can't do it, but you've got to do it with preheat. Well, if you're going to go and preheat it, it's going to be faster to wire tie it. So most people wire tie it, particularly now that you got the epoxy on there. So it's not that often that people tack weld it, although I still see it on non-epoxy coated rebar every now and then. Probably once every 3 or 4 years, someone brings me a piece of broken rebar. They don't always bring down a building during construction, and that one guy broke his leg, some concrete fell on him, and nobody got hurt. But it would have been really embarrassing if the building had been completed, as far as that goes. So Dan Rather had to wait another year to get into his building. Big deal. Oh, if you get to cast iron, this is a guide, okay, the lowest level here. And it turns out cast iron's got like 3 or 4% burden. And here's a plot of preheat for cast iron. In cast iron, you can get to 700 degrees preheat. Now, who wants to weld on a piece of steel that's at 700 degrees? It's like standing next to an open oven. Okay, now, when the Seawolf submarine had its problems with hydrogen cracking, with these very small little cracks in the weld metal, the initial solution to get back in service for about the first 6 months or a year was to actually preheat these things to 400 degrees Fahrenheit. They had been preheating to about 200 degrees, but depending on the carbon equivalent down here, so this is carbon equivalent versus no crack temperature, okay? So up above this, you don't get a crack, below you do, and here are your cast irons, but they actually, for the submarine steel, they didn't have the carbon equivalent this high, but it turns out because of higher strength of cast irons, they were welding with 200 degrees preheat. They had to go up to 400 degrees until they got everything under control about a year later. And it turns out the welders, if you've ever seen a submarine, there's lots of little compartments. And so a lot of times it's kind of like trying to weld underneath that chair. The guys had to crawl in there. They had to bend the electrodes, like I show you over there, in order to even reach where they want to weld in some of these cases. So how would you like to go into one of those things that's preheated to 400 degrees? They basically had people in what they call blue jelly suits. And a blue jelly suit is this gel, and they would pump liquid through the suit. They'd put you in the suit, which was an air conditioner, you know, basically a fluid air conditioner, if you will, not air conditioner, but a fluid conditioner. And they would pump cold fluid through the suit because they were sending you into a 400-degree oven. And you have to wear a mask because you don't want to be breathing 400-degree air into your lungs. You'd have to breathe through a mask. And this is how they were welding the submarine together for about the first 6 months before they finally got the preheat down to manageable levels by controlling the carbon in the welding electrode and some other things. But they couldn't afford to have a second failure. Congress would cancel the whole program. So they went to huge extremes in order to do things. This is a similar type of plot. You say, gee, it looks like the plot he just showed me for the cast irons. But it's not. This actually is I think from the Structural Welding Code Appendix. But here's your carbon equivalent formula: preheat temperature to avoid hydrogen-induced cracking versus carbon equivalents. And it's got a nice steep slope like this. It only goes up to, well, it does go up to 400 degrees. And it shows a bunch of different steels in here. Okay? So you have to know which steel you're welding. There are recipes, they're well known. Still, officially, each company is responsible for their own recipe. Now, that's that type of steel. Stainless steels get a little bit different. This is a book that just came out. I got this about 2 weeks ago, 2005. It's written by John Lippold, who's a professor at Ohio State, head of the welding engineering department there right now, and Damien Katecki. Damien Katecki has spent the last 30 or 35 years of his life looking at welding of stainless steels, first for one welding electrode manufacturer and now for Lincoln Electric, which is the largest one in the world. And so there's a whole book on welding of stainless steels, and I'm not going to go through all the details. There are three, well actually they list 4 general types of stainless steels. One is austenitic, which is non-magnetic, which is very easy to weld. However, I think I told you once before that I found that even though stainless steels are only about 5% of all the steels made, they're about 30% of all the problems. Because everybody thinks that stainless steels will never oxidize and will never corrode. Well, it depends, okay? Turns out austenitic stainless steels are relatively easy to weld in terms of a welding procedure specification, the recipe for actually making the weld. But then making a weld that won't corrode is another complexity to it, and so that makes things a lot harder. Then there's ferritic stainless steels, which are magnetic. And ferritic steels have the same crystal structure as your regular carbon steel, only they have lots of chrome, so they're difficult to weld, and you have to worry about hydrogen cracking. Okay, just like you had that, okay? Here, there's no hydrogen problem. In fact, one of the solutions when you're having a hard time welding carbon steels without hydrogen cracking is to use austenite filler metal, because the austenite dissolves lots of hydrogen and holds it in. It has like 10 times the solubility for hydrogen and doesn't release it into the base material where the cracking usually occurs. Okay? Supposedly, when they first started welding the Nautilus submarine or some of the early prototypes in the 50s with higher strength steels, they couldn't solve the problem. They really just didn't have the technology at the time we do today. And so they ended up, just to keep things on schedule, they welded with austenitic weld metal, which led to corrosion problems because you have dissimilar metals now, and also lowered the diving depth of the submarine, because these are not as strong as these. That's one of the reasons we use these. And then there's martensitic, and these are very difficult to weld because they have higher carbon, so they have a higher carbon equivalent, and they are a similar crystal structure, and they are susceptible to hydrogen cracking. So they're very difficult, but they can be welded. And the last one is duplex, and duplex is actually a mixture of these two, right here, austenite and ferrite, has very good corrosion resistance, high strength, particularly in very good corrosion resistance in hydrogen sulfide, which is really just a form of hydrogen cracking. So you could give a whole course, and I suspect that John Lippold does at Ohio State, on welding of stainless steels. So that may be, we can start talking about aluminum. There is a structural welding code for aluminum, which has the same set of, or actually has a different set of design rules. Okay, because for aluminum, somewhere in here, I had something on aluminum. Oops. No, I took it off. Anyway, here it is. There are lots of different aluminum alloys, just like there are lots of different steels. One of the things that characterizes different aluminum alloys is the amount of alloying element. So here's the alloy designation. The 1000 series means mostly pure aluminum, not too much other alloying element. If you look across here, there's not much of, these are all less than 1%. 3000 series is also fairly low, but a little bit higher. It's actually got a fair amount of manganese in it. This is what I call beer can stock. Okay, they use it for other things like cooking utensils and stuff. But the 3000 series, very large volume of it made because 40% of all aluminum goes into packaging. 4000 series, typically these are your weld metals, highly alloyed with silicon. Essentially, they're very similar to aluminum casting alloys. 5000 series are aluminum manganese alloys, or magnesium alloys, and so they have high amounts of magnesium. They can have little bits of chrome and manganese and other stuff in them, but basically they're solution hardened. These are kind of your marine grades are in here. They're not heat treated. And then I didn't give you the next page of this. This is just one page of the aluminum alloys. There would be the 7000 series and the 6000 series, which are the ones that are heat treated. And it turns out no one until now, supposedly friction stir welding, no one could get 100% strength of the 6000 and 7000 series aluminum alloys. Okay, so I got all these different alloys. Actually, I forgot this board works. 1000 series is pure aluminum, basically fairly weak. 3000 series is also fairly weak. Oh, I didn't mention the 2000 series is copper alloys, not generally not weldable. There are like 2219, the space shuttle made tanks made out of 2219 and is welded, but anyway. 4000 is welding electrodes, primarily. 5000 is solution hardened. And they'll have a strength, a tensile strength, of about 40 KSI. The 6000 and 7000 are heat-treated, aged, precipitation heat-treated. The 6000 series might be 50 to 60 KSI tensile strength, and the 7000 series will be up to 7,000. There's an 8,000, there's 9,000 series, but they're kind of specialized. We don't run across them much. Well, not for welding anyway. The 8,000, I think, include the aluminum lithium alloys for aircraft structures. Anyway, you can weld these and get 100% strength. These, you're lucky to get 50% strength because the heat effective zone gets unheat treated, okay, by the welding process. So if you do fusion welding on these guys, you're out of luck. You won't get full strength. So the aluminum guys have come up with lots of different designs, and I've loaned my welding stuff to somebody else. But let's say I got aluminum tubes, and if I want to weld the structure with aluminum tubes out of high strength alloy, I essentially will use gusset plates that kind of look like this. I might have another one down here. And I'll put welds, fillet welds in over here. And if I do this properly, I can get just as much strength even though the weld metal is half as strong as the base material, because the intersection of all these tubes comes into a gusset plate that bears the stress. And then I can have a nice long fillet weld compared to anything I just had along the length here. It's a more expensive structure, more welding, but I can use the high strength aluminum alloys so far as that goes. Now the main thing in aluminum alloys is, depending on which one of those alloys you want to weld, you will get cracking. Not hydrogen cracking, but a different form of cracking called hot cracking. And if I go, this is the welding handbook. If I go to the aluminum guide to the selection of filler metal for general purpose welding, here's my 1000, 2000, 3000, 5, 6, casting alloys down here. And here are my, if I'm going to weld this to this or this to this, so different aluminum alloys across here, different ones down here. and I go across here, and it will tell me which welding electrode, and they typically will be 5,000 or 4,000 series electrodes or 1,000 series electrodes. Okay? Now all of that can be understood fairly simply by looking at the phase diagram for aluminum. It doesn't really matter whether you're looking at aluminum silicon, aluminum copper, aluminum magnesium. Aluminum, this is temperature, this is percent X in the alloy. They form eutectics with all these other things. So this is 661, that's the melting point on aluminum in degrees centigrade. This is going to be down around 520 or something like that. If I'm a very lean alloy with only a couple of percent, my solidification range from liquid to solid is this temperature difference. If I'm near the eutectic, it's also similarly small, okay, between liquid and solid. In this intermediate region, I've got a much bigger solidification range. And aluminum actually shrinks about 6% on solidification. So if I have this rigid aluminum structure and the weld metal wants to shrink, when it's like a Slurpee, it's in the liquid-solid region. If I have a big liquid-solid region, I have a bigger delta T, and a bigger delta T means more solidification shrinkage. So I'll just rip that Slurpee apart due to the shrinkage stresses. It's all proportional to the delta T. Okay? If I have a small delta T, not a problem to weld it. So over here, very highly alloyed or very leanly alloyed, I can weld it. If I end up with a weld metal in the middle here, I'm out of luck. A lot of the aluminum copper alloys are designed to be in here for optimum strength. That's why they're not weldable. They don't fail in the weld metal, they fail in the base material. I have a lot of welding electrodes, the 4000 series, where I just dump in 10% silicon into the welding electrode, and that means that that weld metal is going to be highly alloyed no matter what. I always have a small delta T. I have some other alloys, some 1000 series welding electrodes that are nearly pure, and I could weld the 1000 series or the 3000 series with those and have a small delta T. But if I take a lightly alloyed base plate, like a 3000 series, and try to weld it with a 4000 series, I'm going to end up with a weld metal that's halfway in between. It's going to crack, right? So you want to avoid this region in here. Don't weld with a composition that ends up in between with big delta T's. Be over near here or be over near here. That's all that table tells somebody, although it doesn't tell them. This is going out to general purpose people, like welding inspectors or something, or structural engineers who don't understand the metallurgy of what's going on here. But that's what this table is all about. They're basically pre-selecting, either use a highly alloyed weld metal or a very lightly alloyed weld metal, depending on the base metal that you're welding. Okay? So that's how you weld aluminum. See you tomorrow.